You live on a planet 7,900 miles across. That planet orbits a star so wide that 1.3 million Earths could fit inside it. That star sits inside a galaxy containing 400 billion stars. A galaxy so vast that light itself needs 100,000 years to cross it from edge to edge. That galaxy belongs to a cluster of dozens of galaxies called the Local Group, which is part of a supercluster called Laniakea stretching 600 million light-years in every direction. None of that prepares you for the Boötes Void. Nothing does. The Boötes Void is a region of space so empty, so incomprehensibly vast, that astronomers who first encountered it in the data assumed they had made an error. They had not made an error. The void is real, it is measured, and its scale does not become any easier to accept no matter how many times you encounter the numbers. The Boötes Void is a sphere of nearly empty space approximately 330 million light-years across. To call it large is to say the Pacific Ocean is damp. In the known universe, structures of this scale are not supposed to exist. The physics of cosmic formation, the models that describe how matter clumped together from the soup of the early universe, the computer simulations that reproduce billions of years of gravitational history, none of them predict a void this wide, and yet it is there, sitting in the direction of the constellation Boötes, roughly 700 million light-years from the Milky Way, waiting in silence. It has no stars, it has no nebulae, it has no galaxies to speak of. It has nothing on a scale that the word nothing cannot hold. There is a specific quality of dread that arrives when you begin to truly calculate the Boötes Void. It is not the dramatic dread of danger, it is quieter. It is the dread of encountering something so far outside the range of human perception that your brain simply refuses to fully accept it. You can say the words 330 million light-years. You can write the number. You can read it aloud. But the understanding, the actual gut-level comprehension of what that distance means in physical terms, that understanding will not come easily. This script is an attempt to build it piece by piece from the ground up. By the end, you will not feel smaller. You will feel differently about what scale itself means, and about what it tells us that we can measure at all. If you enjoy deep space documentaries that take the biggest questions in the universe seriously, do me a favour and hit that like button and subscribe. It helps more than you know, and it lets me keep making content like this for all of you. I genuinely appreciate every person who takes the time to listen. Now, get yourself comfortable. Let us begin at the beginning. In 1981, a team of 4 astronomers at the Harvard-Smithsonian Center for Astrophysics was doing something that had never been done before on this scale. They were mapping the universe, not the part of the universe near Earth, not the local neighborhood of galaxies. They were systematically measuring the positions of thousands of galaxies hundreds of millions of light-years away, recording their distances, and building a 3-dimensional picture of cosmic structure that no one had ever seen clearly before. The team consisted of Robert Kirsch Nier, Augustus E.M. Löhr Jr., Paul Scheck Ter, and Stephen Scheck Tman. They were working from a theoretical framework that expected to find the universe roughly uniform at large scales, a smooth cosmic fabric punctuated by clumps and clusters, but broadly even in its distribution of matter. They expected to see galaxies more or less everywhere, varying in density, but present throughout. The method they used was redshift spectroscopy. When a galaxy moves away from us, its light is stretched to longer wavelengths by the expansion of space. The faster the recession, the greater the redshift. Because the universe is expanding uniformly in all directions, a galaxy's recession speed is directly proportional to its distance. Measure the redshift and you know the distance. With enough measurements, you can build a map. The team pointed telescopes at a narrow strip of the sky in the direction of the constellation Boötes, then measured the redshifts of every detectable galaxy in that strip with painstaking precision. Each galaxy required careful observation, its spectrum recorded on photographic plates, then analysed to extract the precise shift in the wavelengths of known chemical emission lines. The work was slow. The data came in over months, and at first it looked like what everyone expected. The selection of the Boötes region for the original survey was not driven by any expectation of what would be found there. It was driven by the practical requirements of observational astronomy. The constellation Boötes sits high in the northern spring sky, well above the plane of the Milky Way, in a direction that astronomers call the Northern Galactic Cap. This positioning has a specific observational advantage. The Milky Way is filled with gas and dust, and this material scatters and absorbs light from distant galaxies, making them harder to detect and introducing systematic errors into redshift measurements. In the directions that look out perpendicular to the Milky Way's disk, this foreground contamination is minimized because the path through our own galaxy is shortest in those directions. Surveys looking toward the galactic poles encounter the least possible interference from our galaxy's own material. The Kirch-Near team chose Boötes in part for this reason. It offered a window through which distant galaxies could be observed with minimal obstruction from our galaxy's gas and dust. This was not a unique consideration. Other teams conducting redshift surveys in the same era chose similar regions for the same practical reasons. The Northern Galactic Cap is a well-known clean window on the extragalactic universe, and it had been used in prior surveys that the Kirch-Near team was extending. The team was not looking for a void. They were conducting a methodical census of the galaxy population in a well-chosen survey strip, the angular boundaries of which were set by practical considerations of telescope scheduling and observing efficiency rather than by any specific prediction about what the region might contain. The void was found because the survey happened to be pointed there at the right depth, with enough sensitivity to detect the profound absence it revealed. No deliberate search for extreme voids was being conducted. The void presented itself in a dataset assembled for entirely different scientific purposes, which is how many of the most significant discoveries in astronomy have arrived. And then they hit the gap. Not a gap in their data, not a gap in their observations, a gap in the universe. At a certain range of distances in their survey slice, roughly between 500 million and 800 million light-years from Earth, galaxies simply stopped appearing. The redshift measurements that should have been populating that band of space with the expected density of cosmic objects came back nearly blank. A handful of detections, then nothing. Then on the far side of the gap, galaxies again. The initial assumption was equipment error. The initial assumption is always equipment error. They checked the plates. They reran the calculations. They looked for contamination in the data. Systematic biases that might cause a false void in the measurement. They found nothing wrong. What they were seeing was not a gap in the data. It was a gap in reality. The technical process of measuring redshifts from galaxy spectra in 1981 was painstaking in ways that the automated surveys of the following decades have made difficult to appreciate. Each galaxy observation began with pointing the telescope at the target and guiding it carefully for the duration of the exposure, which might last from 30 minutes to several hours depending on the galaxy's brightness and distance. The light from the galaxy passed through a spectrograph, which used a diffraction grating to spread the incoming light into its constituent wavelengths, creating a spectrum on a photographic plate. On that spectrum, absorption lines appeared at specific positions, produced by chemical elements in the galaxy's stars and gas absorbing light at characteristic frequencies. To measure the redshift, the astronomer had to identify these lines, compare their measured wavelengths to the known laboratory wavelengths of the same elements, and calculate the fractional shift. A calcium absorption feature that should appear at a specific wavelength in a laboratory source, but was observed shifted significantly toward the red end of the spectrum in a distant galaxy, revealed that galaxies' recession velocity, and therefore its distance. The measurement required careful calibration of the spectrograph using reference lamps whose emission lines were known precisely. It required measuring the positions of spectral features on photographic plates with a precision of fractions of a millimeter. Using devices called comparators that traced the plate mechanically and recorded the position and intensity of each feature. For the Kirchner team working in 1980 and 1981, this was largely manual work. Spectra were measured one by one, calculations performed with hand calculators or early computers, and results compiled into catalogues maintained in printed form and updated as new observations came in from the telescope. The cumulative effect of hundreds of these measurements, each requiring hours of telescope time and careful analysis, was the dataset from which the void's absence emerged, not as a dramatic moment of discovery, but as a statistical pattern that gradually became impossible to dismiss. The paper they published that same year sent a shock through the astronomy community. Not because the idea of voids was new. Astronomers had known for some time that the large-scale structure of the universe contained regions of lower galaxy density alongside denser clusters and filaments. But voids of the size this team was reporting had no precedent. The physics of how structure forms in the universe did not easily allow for an empty region this large. The gravitational dynamics that pull matter together and push it apart, working over the full 13.8 billion year history of the cosmos, simply should not have been capable of producing something this enormous and this empty. Colleagues were skeptical. Some dismissed the finding as a sampling artifact, a consequence of the narrow survey strip they had used. Others pointed to the relatively small number of galaxies sampled. The debate was sharp and it was not resolved quickly. What followed over the next decade was a series of independent surveys designed to confirm or refute the Kirchner team's finding. Different telescopes, different sky positions, different methodologies. Each new survey pointed its instruments at the region in question and came back with the same result. The void was there. The independent confirmations piled up. By the early 1990s, the Boötes Void was no longer a controversial claim. It was a feature of the universe, a real, measured, verified feature that existing theory struggled to explain. Astronomers continued to catalogue it, to refine its dimensions, to count the galaxies inside it more carefully, and to study its relationship to the surrounding cosmic structure. Each study sharpened the picture. Each study made the void harder to dismiss and harder to explain. The confirmation of the Boötes Void unfolded alongside a broader revolution in how astronomers visualize the large-scale structure of the universe. In 1986, 5 years after the Kirchner team's original announcement, Valerie de la Parahen, Margaret Geller and John Hook Ra, also at the Harvard-Smithsonian Center for Astrophysics, published a redshift survey of a thin slice of the northern sky that produced what immediately became one of the most famous images in the history of cosmology. Their survey covered a strip of sky 2 degrees wide and 135 degrees long, containing more than 1,000 galaxies out to a distance of roughly 250 million light-years. When they plotted those galaxies in redshift space, using recession velocities as a proxy for distance, the resulting diagram showed something no one had anticipated with such visual clarity. The galaxies were arranged not in a smooth or random distribution, but concentrated on the surfaces of enormous curved structures, like the skins of bubbles, leaving the interior volumes nearly empty. Voids appeared at multiple scales across the diagram, and the galaxies traced their boundaries in a pattern that immediately suggested a foam-like architecture to the universe at these scales. This image was described in exactly those terms, and the foam analogy caught on at once. The universe at the scale of hundreds of millions of light-years resembled a cosmic foam of bubbles, each bubble an evacuated void, its surface made of the concentrations of galaxies, filaments, and sheets that define the cosmic web. The picture was immediately compelling not just to astronomers but to anyone who looked at it, because it made visible what had previously been abstract. The Boötes Void, discovered 5 years earlier, fit into this picture as its most extreme confirmed example. Not a soap bubble, but something so much larger that placing it in the foam diagram required stepping back to a scale at which ordinary bubbles vanished from view. The Harvard-Smithsonian surveys continued expanding through the late 1980s, eventually producing the CFA2 catalogue, which covered a broader portion of the sky and measured the redshifts of more than 18,000 galaxies. From this dataset, Geller and Hook-Ra announced another landmark discovery in 1989, the Great Wall. The Great Wall was a massive sheet of galaxies stretching at least 500 million light-years across the northern ski, one of the largest concentrations of matter ever measured at the time of its announcement. It lay at a distance of roughly 200 to 300 million light-years from Earth, far closer than the Boötes Void but comparable in linear extent. The Great Wall demonstrated that the universe could organize matter into structures that, in their spatial reach, rivaled the scale of the Boötes Void itself, though opposite in character. The void was defined by absence. The Great Wall was defined by extraordinary excess. Both structures sat at the limits of what the theoretical models of the time predicted should be possible. The discovery of the Great Wall reinforced the lesson of the Boötes Void. The universe at large scales was not homogeneous or bland. It was organized into features of extraordinary scale on both extremes, the concentrated and the evacuated, the dense and the empty. And the two types of extreme structure were not independent. Every void was bounded by the walls and filaments that the matter evacuated from it had built elsewhere, and every wall was hollowed out on its interior-facing sides by the pressure of matter flowing outward into the surrounding density. The Great Wall and the Boötes Void were part of the same process, the same cosmic web, expressing its two extremes in adjacent regions of the same universe. Together they established that the large-scale structure of the cosmos operated on scales that demanded more ambitious observational programs and better theoretical frameworks than had existed before their discovery. The technological transformation that made the next generation of large-scale structure surveys possible was the development of multi-fiber spectroscopy, which fundamentally changed the economics of redshift survey work. In the original CFA surveys, each galaxy's spectrum was measured one at a time. The telescope pointed at a single galaxy, the spectrograph exposed, the plate developed and analysed, and only then could the instrument move to the next target. This imposed a hard limit on survey speed. No matter how efficiently a team operated, only a limited number of galaxies could be measured per observing night. Multi-fiber spectrographs removed this constraint by placing dozens or hundreds of optical fibers across the wide focal plane of a telescope, each fiber directed at a known galaxy and carrying its light to a common spectrograph. In a single exposure, 100 or more galaxy spectra could be recorded simultaneously. The 2-degree field galaxy redshift survey conducted at the Anglo-Australian Telescope in New South Wales during the 1990s and early 2000s used this approach to measure nearly 250,000 galaxy redshifts across both hemispheres of the sky. The Sloan Digital Sky Survey, operating from a dedicated telescope in New Mexico, with a camera that imaged a 3-degree field and a spectrograph that observed 640 objects per plate, eventually catalogued more than 3 million astronomical objects. These surveys operated at scales that would have required decades using the single galaxy methods of the 1981 Kirch-Near survey. They produced 3-dimensional maps of the galaxy distribution across volumes of the universe many times larger than any prior survey. The Boötes Void appeared in these maps as a precisely characterized feature, its dimensions refined by far more numerous data points than the original detection, its interior population catalogued to fainter galaxy luminosities and its surrounding filaments and walls traced with the detail needed to understand the void's place in the large-scale architecture of the cosmic web. The large-scale structure surveys of the 1990s and 2000s did not merely confirm the existence of individual structures like the Boötes Void. They provided, for the first time, the statistical power needed to characterize the full distribution of cosmic voids and compare it quantitatively with the predictions of cosmological theory. The primary tool for this comparison is the matter-power spectrum, a mathematical function that describes how the amplitude of density fluctuations varies with spatial scale across the observable universe. On small scales, the universe is strongly inhomogeneous. Galaxies cluster, groups merge, filaments concentrate matter into dense nodes. The power spectrum amplitude is high at small scales, reflecting large density contrasts. At large scales, the fluctuations become smaller on average, and the universe approaches the broad homogeneity expected at very large distances. The specific shape of the power spectrum, the way its amplitude falls from small to large scales, is sensitive to the fundamental cosmological parameters: the density of ordinary matter, the density of dark matter, the properties of dark energy, and the character of the inflationary process that set the initial fluctuations in the first fraction of a second after the Big Bang. By measuring the power spectrum from large redshift surveys, cosmologists can constrain these parameters with increasing precision. Voids like the Boötes Void enter this framework as constraints on the low-density tail of the distribution. A cosmological model that correctly predicts the observed power spectrum must also correctly predict the distribution of void sizes. If the predicted void size distribution does not comfortably accommodate voids at the scale of the Boötes Void, that represents tension with the model. If it does accommodate such voids but only at the extreme statistical tail, that tells us the model is being tested at its limits. The Boötes Void is, in this sense, a constraint as much as a curiosity, a data point that tests whether our understanding of the universe is complete. The cosmic web is the name given to the large-scale structure of the universe, and it is precisely that, a web. If you could step back far enough to see the entire observable universe at once, what you would see is not uniform. You would see an intricate 3-dimensional network of filaments, each one a strand of matter stretching across hundreds of millions of light-years, containing thousands of galaxies linked by gravity, gas, and dark matter. Where multiple filaments meet, you find superclusters, the most massive gravitationally bound structures in the universe, sprawling concentrations of galaxies and galaxy groups that mark the nodes of the web. And between the filaments, between the nodes, between every strand of this cosmic network, you find voids, dark, empty, enormous. The voids are not gaps in the structure, the voids are the structure. To understand voids, you need to understand how the cosmic web came to exist in the first place. In the earliest moments of the universe, matter was not distributed perfectly evenly. There were tiny fluctuations, almost imperceptible variations in density, etched into space by quantum processes in the first fraction of a second after the Big Bang. These fluctuations were infinitesimally small, but gravity is patient and gravity is relentless. Regions that were slightly denser than average attracted more matter than their surroundings. Regions that were slightly less dense than average began to empty out as their matter drained toward the denser zones. Over billions of years, the slightly dense became more dense, and the slightly sparse became more sparse. The filaments formed where matter converged. The voids formed where matter departed. The whole architecture of the cosmic web is, at its root, the amplified memory of quantum fluctuations from before the first second of time. Typical cosmic voids are not small. Even an ordinary void, the kind that populates the cosmic web in large numbers, might span 50 to 100 million light-years across. These are not trivial structures by any measure. If you stood at the center of an ordinary void and aimed the most powerful telescope ever built in any direction, you might find no galaxy within 50 million light-years of you. That is already a scale that exceeds comprehension by most definitions. But ordinary voids have a known explanation. They fit within the predictions of the models. Gravity over the age of the universe can evacuate a sphere 100 million light-years in diameter. The math works. The simulations reproduce them. Ordinary voids are strange, but they are understood. The Boötes Void is not an ordinary void. The mechanism by which voids form is, in its essentials, the reverse of the mechanism by which galaxy clusters form. Both processes are driven by the same force, gravity. In regions where the primordial density was slightly above the cosmic average, gravity amplified the excess over billions of years, drawing in surrounding matter and building the filaments, walls, and superclusters of the cosmic web. In regions where the primordial density was slightly below the cosmic average, the opposite process unfolded. Matter in the underdense region experienced a weaker gravitational pull from its immediate surroundings than matter in the denser adjacent regions. Over time, this imbalance caused matter to flow outward, draining from the underdense region toward its overdense surroundings. As the region lost matter, its density dropped further, creating a larger contrast with the surroundings and accelerating the outflow. The process is self-reinforcing in the same way that gravitational collapse is self-reinforcing. A slightly underdense region becomes more underdense, which causes faster outflow, which makes it more underdense still. Over the full 13.8 billion years of the universe's history, this process has produced the range of void sizes observed today. Small regions that were initially and modestly underdense have become ordinary voids of tens of millions of light-years. Large regions with deeper initial underdensities have become supervoids. The critical question for the Boötes Void is whether the initial underdensity in its region was itself exceptional relative to the expected distribution of primordial fluctuations, or whether the ordinary range of initial quantum variations can, given enough time and the right cosmological conditions, produce an evacuated region of that extraordinary scale. This question connects the present-day observable properties of the void directly to physics operating at energies and timescales billions of years before any galaxy existed, in the first fractions of a second after the Big Bang. Dark matter plays an essential and often underappreciated role in both the formation and the character of cosmic voids. Unlike ordinary baryonic matter, which interacts through electromagnetic forces and can be heated, cooled, compressed, and assembled into stars by radiative cooling, dark matter interacts only through gravity. It cannot radiate energy, cannot form compact objects through electromagnetic process, and does not participate in the nuclear and chemical reactions that build the luminous universe. But it constitutes approximately 27% of the total energy density of the universe, compared to roughly 5% for ordinary matter. and this numerical dominance in the matter budget means that dark matter sets the gravitational template on which all cosmic structure forms. In the early universe, before the formation of the first stars and galaxies, dark matter had already begun to organize itself under the influence of the primordial density fluctuations. Regions destined to become galaxy clusters first assembled as dark matter halos, gravitational wells into which ordinary matter later fell and condensed into stars. Regions destined to become voids were already underdense in dark matter, and this deficit of gravitational scaffolding was what allowed ordinary matter to drain from them without the framework needed to retain it. The interior of the Boötes Void is almost certainly underdense in dark matter in proportion to its galaxy deficit. The ordinary matter that should be inside the void in the form of galaxies, and the dark matter that should be providing the gravitational halos to host those galaxies, were never present in sufficient quantity to prevent the region from evacuating over cosmic time. To fill the Boötes Void with galaxies, you would first need to fill it with dark matter halos, and those halos were not in the primordial density field that seeded the structure we observe today. The void's emptiness goes deeper than its galaxy census suggests. The relationship between a void's final size and the initial conditions that produced it is not simply proportional, and this nonlinearity is important for understanding why the Boötes Void poses such a challenge to standard models. A void 3 times larger than a typical example did not necessarily start from an initial underdensity 3 times deeper. The amplification of density contrasts by gravity over cosmic time is a nonlinear process, and small differences in the initial density field can produce dramatically different outcomes by the present day, especially at the large spatial scales relevant to supervoids. Computer simulations that attempt to reproduce the observed large-scale structure of the universe, the n-body codes that evolve billions of dark matter particles from initial conditions derived from the cosmic microwave background, can reproduce the cosmic web in its broad outlines with impressive accuracy. They produce roughly the right distribution of galaxy clusters, filaments, and voids when started from cosmologically motivated initial conditions. But when these simulations are examined specifically for voids at the scale and depth of the Boötes Void, they produce such structures rarely. The frequency with which Boötes scale voids appear in standard Lambda-CDM simulations is much lower than would be expected if the Boötes Void were a typical member of the void population. It sits at the extreme end of the statistical distribution, where the standard model begins to strain against observations. This tension has been recognized since the void was confirmed in the late 1980s and has not been fully resolved since. Whether it reflects a genuine incompleteness in the standard cosmological model, a problem with the assumed properties of dark energy, or the initial power spectrum, or whether the Boötes Void is simply the rare but theoretically possible extreme of what the standard model can accommodate, remains one of the most carefully examined open questions in the study of large-scale structure. At 330 million light-years across, the Boötes Void is more than 3 times the diameter of a large typical void. This sounds like a modest difference. It is not. Because volume scales with the cube of the radius, a sphere 3 times as wide contains 27 times as much volume. The Boötes Void is not 3 times as remarkable as a large ordinary void. It is 27 times as volumetrically empty. The amount of matter that must have moved out of this region to produce its observed galaxy deficit is not 3 times what you would expect from a standard void. It is an order of magnitude beyond that. And the question that has never been satisfactorily answered is this: where did it all go, and how did it get there so quickly? Let us build the scale comparison step by step, because the number 330 million light-years needs to be translated into something the mind can engage with. Start with the Milky Way. 100,000 light-years across. That is our home galaxy, and it is not a small galaxy. It contains 400 billion stars, hundreds of billions of solar masses of gas and dust, and its disk is so wide that a beam of light entering one edge would take 100,000 years to emerge from the other side. By any human standard, the Milky Way is incomprehensible in its size. You can live your entire life studying it and never run out of things to learn. Now take the Boötes Void. You would need to line up 3,300 Milky Way galaxies edge to edge to span the diameter of the void, not copies of a few galaxies, 3,300 Milky Ways. The local group, the cluster of galaxies to which the Milky Way belongs, spans roughly 10 million light-years. It contains more than 50 galaxies including Andromeda, the Large and Small Magellanic Clouds, and dozens of smaller dwarf galaxies. 10 million light-years feels enormous compared to the Milky Way. But the Boötes Void would contain 33 local groups lined up across its diameter. The entire gravitational province of the Milky Way, every galaxy we are cosmically bound to, every object in our neighbourhood of space, could fit inside the Boötes Void 33 times over, end to end. And the void would still be the same vast empty sphere it has always been. None of those galaxies, none of those gravitational bonds, none of that cosmic neighbourhood context would register as anything other than an infinitesimally thin slice of the void's immensity. The Virgo supercluster is the supercluster that contains our local group. It spans roughly 110 million light-years and contains at least 100 galaxy groups and clusters. It is the structure above the local group in the cosmic hierarchy, and it dwarfs everything within it. The Boötes Void would contain 3 Virgo superclusters lined up across its diameter. The entire supercluster, with all its galaxies, all its dark matter halos, all its gravitational complexity, would fit into the void 3 times. Laniakea, the even larger supercluster of which the Virgo supercluster is only a small part, extends roughly 600 million light-years. The Boötes Void is roughly half the diameter of Laniakea, a feature that was discovered because it seemed to empty as roughly half the size of the largest known gravitationally bound structure associated with our cosmic address. Now translate the diameter into time. Light travels at approximately 186,000 miles per second. It is the fastest thing in the universe. A beam of light crossing the Boötes Void would take 330 million years to complete the journey. To give that number something to grip on, consider that 330 million years ago, Earth had not yet seen its first mammals. The Triassic period had not begun. The continents were arranged differently. Complex life had just begun its recovery from the Permian extinction event, the largest mass extinction in Earth's history. If a photon of light had begun crossing the Boötes Void at the moment life on Earth was rebuilding from that catastrophe, it would only just be reaching the other side right now. The crossing time for this void is older than the oldest mammal, older than the first dinosaur, older than the first turtle. If you were travelling in a spacecraft at the speed of the fastest probe humanity has ever built, the Parker Solar Probe, which achieves speeds of about 430,000 miles per hour, you would need roughly 500 trillion years to cross the Boötes Void. The observable universe is approximately 13.8 billion years old. You would need more than 36,000 times the current age of the universe to make that crossing. You would arrive in a future so remote that every star in every galaxy would have long since burned out. The universe would be dark, cold, the last black holes would be evaporating, and you would still be crossing the void. That is not an exaggeration. That is arithmetic applied to real measured numbers. Within the Boötes Void, astronomy has identified approximately 60 known galaxies. 60, in a volume that, based on the average density of the surrounding universe, should contain something in the range of 2,000 galaxies. By some estimates, that number is even higher. The galaxy deficit inside the Boötes Void is not merely a statistical anomaly, it is a fundamentally different cosmos. If you mapped the galaxies of the surrounding universe at their typical density, you would expect to find a galaxy every few tens of millions of light years in any direction. Inside the Boötes Void, you can travel for hundreds of millions of light years and find almost nothing. The 60 galaxies that do exist inside it are not evenly distributed through its interior. They cluster near the outer edges, arranged in a loose shell, as if the void has pushed whatever matter remained in it toward its own walls. This shell structure is one of the most scientifically interesting features of the Boötes Void. The 60 or so galaxies inside it are not randomly sprinkled through the void's volume. They trace the inner boundary of the void, sitting along the rim where the empty interior transitions back to the denser filaments and walls of the surrounding cosmic web. This arrangement suggests that the void is not simply a region that started empty. It behaves as if matter has been evacuated from the center outward, or drawn toward the denser regions outside through gravity's steady pull over billions of years. Some models suggest that voids actively grow over time as the matter on their edges is drawn away by surrounding overdensities, leaving the center increasingly empty. In this reading, the shell of galaxies in the Boötes Void marks the active boundary of the void's ongoing expansion. The observable universe spans roughly 93 billion light-years in diameter. Within that sphere, there are estimated to be 2 trillion galaxies. The Boötes Void's diameter is approximately 330 million light-years, which makes it roughly 0.35% of the observable universe's diameter. That sounds like a small fraction, but remember that volume scales with the cube of linear dimensions. The void occupies a volume of space that, if every cubic light-year of it were somehow filled with galaxies at the average cosmic density, would contain more than 2,000 galaxies. Instead, it contains 60. The void is not just big, it is disproportionately empty relative to anything that has been modelled or predicted by the standard framework of cosmological structure formation. The standard cosmological model known as Lambda-CDM, which stands for Lambda Cold Dark Matter, is the most successful framework we have for describing the large-scale structure of the universe. It incorporates the effects of dark matter, which provides the gravitational scaffolding for cosmic structure, and dark energy, which drives the accelerating expansion of space. Lambda-CDM has been tested against observations of the cosmic microwave background, the distribution of galaxy clusters, the large-scale structure surveys, and the expansion history of the universe. In each domain, it performs remarkably well. Its predictions match observations at a level of precision that earns it the designation of a standard model. But when it comes to the Boötes Void, Lambda-CDM begins to show strain. The maximum size of a void that gravity can produce in the age of the universe within the Lambda-CDM framework is estimated to be somewhere around 150 to 200 million light-years. This estimate comes from detailed n-body simulations, computer models that simulate the gravitational interactions of billions of particles over cosmic time, tracking how matter moves, where it clumps, and what regions it evacuates. These simulations reliably produce a cosmic web that closely resembles the observed large-scale structure of the universe. They produce filaments and nodes. They produce voids of many sizes, but they almost never produce a void as large as the Boötes Void. When they do, it is at the very extreme tail of the statistical distribution, a once-in-the-observable universe fluctuation that pushes the limits of what the model can accommodate. This does not mean that the Boötes Void disproves Lambda-CDM. It does not. The existence of an outlier does not destroy a statistical model, but it does raise a genuine question. If the Boötes Void is the largest structure the model can accommodate, what does that say about the model's completeness? Could there be a physical mechanism that produces large-scale voids more efficiently than standard gravity working on cold dark matter? Could dark energy, which we understand only in its gross effects rather than its fundamental nature, be playing a role in evacuating these regions more efficiently than the simplest models predict? These are not fringe questions. They are active areas of research in modern cosmology, and the Boötes Void is one of the key test cases. The question of how the Boötes Void formed has several candidate explanations, none of which fully satisfies the observational evidence. The first is simply that the void is an extreme but possible fluctuation within Lambda-CDM. On this view, the void is rare but not impossible, a statistical outlier at the far end of what structure formation can produce. The universe is large enough in this argument to contain at least one such outlier. The second explanation invokes the effects of dark energy in a more dynamic form. If dark energy is not simply a cosmological constant but a field that varies in strength across space, it might produce regions where expansion is faster than average, actively pushing matter outward and carving deeper voids than a uniform dark energy would create. This hypothesis goes by various names, including quintessence models and early dark energy proposals. A third candidate involves modified gravity theories. These propose that Einstein's general relativity, while accurate in the solar system and in many cosmological applications, is not the complete description of gravity on all scales. Some modified gravity frameworks predict that gravity's behavior over distances of hundreds of millions of light-years differs subtly from the general relativistic prediction, and that these deviations could lead to faster void formation and deeper evacuation of matter from underdense regions. None of these modified gravity proposals has yet achieved the level of observational support that would elevate them from speculation to established physics. But they are not dismissed, because structures like the Boötes Void keep reminding astronomers that something about our picture may be incomplete. The Boötes Void is not the only supervoid known to astronomers, but it was the first confirmed and remains one of the most studied. The IHRED Achnus supervoid is a more recently confirmed structure, and by some measures it is larger, estimated at 1.8 billion light-years across. But the IHRID Achnus supervoid has a different character. It is shallower in its galaxy deficit, meaning that while it is enormous in spatial extent, it is not as dramatically empty as the Boötes Void relative to expectations. It gained significant scientific attention because of its potential connection to the CMB cold spot, a region of the cosmic microwave background radiation that is measurably cooler than its surroundings and that has resisted straightforward explanation for decades. The proposed connection works through the integrated Sachs-Wolf effect. The integrated Sachs-Wolf effect, or ISW, describes what happens to photons of the cosmic microwave background when they travel through a large supervoid. As a CMB photon enters the near-empty interior of a supervoid, it gains energy, climbing down the shallow gravitational potential well of the void. But in a universe dominated by dark energy, the potential well shifts during the photon's transit, flattening slightly due to the accelerating expansion. When the photon exits the other side, it cannot fully recover the energy it spent climbing back out. It emerges with slightly less energy than it had when it entered. This means it is slightly cooler. The CMB cold spot, a region of the background radiation that is about 0.2 degrees Celsius cooler than its surroundings, may be the imprint of exactly this process as CMB photons passed through a massive supervoid in the early universe. Whether the Iturid new supervoid fully explains the CMB cold spot remains disputed among cosmologists. The size of the effect predicted by the ISW mechanism does not quite match the size of the observed temperature deviation, and some analyses suggest that the void alone cannot account for the full anomaly. But the connection between large cosmic voids and subtle imprints in the CMB is real in principle, and it represents one of the most direct ways that the largest structures in the universe leave measurable traces on the oldest observable signal in the cosmos. The Boötes Void, if a similar analysis were applied to it with sufficient resolution, might leave its own imprint on the microwave background. A faint, cool region corresponding to the vast emptiness it represents. There is another cosmic void worth examining in comparison to the Boötes Void, the KBC Void. Published in 2013 and 2014, the KBC Void is a proposed supervoid of remarkable proportions, roughly 2 billion light-years in diameter, which would make it by far the largest known void in the observable universe. It is also, if confirmed, the void we live inside. The Milky Way, the local group LANI-AHKR, and the broader supercluster complex of which we are part may all reside within a region of space that is significantly underdense relative to the cosmic average. Some studies suggest that our location inside this vast underdensity could account for a discrepancy in the measured expansion rate of the universe, a problem known as the Hubble tension. If we live in a void, the local expansion rate would appear higher than the global rate, because voids expand slightly faster than average regions. The possibility that we inhabit a supervoid is worth pausing on. The Boötes Void, seen from the outside, appears as a vast emptiness in the data, but we cannot see the KBC Void from the outside because we are, potentially, inside it. The way we detect it is by surveying the distribution of galaxies around us in all directions, and noting that there are fewer of them within a radius of about 1 billion light-years than the cosmic average predicts. We infer the void's presence from the deficit in our own neighbourhood. If true, this means that the kind of emptiness we observe in the Boötes Void is not entirely alien to our cosmic address. We may be, on an even larger scale within a similar structure, a different kind of void, shallower in its emptiness but vast in its extent. Now consider what the Boötes Void looks like from the inside of it. Picture a point somewhere near the centre, the deepest region of emptiness. In every direction you look, your nearest neighbour galaxy is hundreds of millions of light-years away. The night sky from this location contains almost nothing. Where the sky, as seen from Earth, contains billions of visible galaxies even in a small patch of space, the sky seen from inside the Boötes Void would be populated by the faint signals of a few dozen galaxies at enormous distances, clustered near the horizon of the void. The closer regions of sky would show only stars from whatever galaxy you happen to be in, and then blackness. Profound blackness. Robert Kirschner, writing about the Boötes Void in a popular account of the discovery, noted that an astronomer living inside the void would have had a very different history of cosmology. From inside the void, with its extreme paucity of nearby galaxies, a civilization that developed astronomy within the time frame that humans developed, it would have found the sky giving up much less information about large-scale structure. The nearest external galaxy would be hundreds of millions of light-years away, which means even with modern instruments like the Hubble Space Telescope, that civilization would see only the faintest smudges where galaxies should be. The discovery of other galaxies, the fundamental realization that the universe contains structures beyond our own, would have been delayed by centuries perhaps. The cosmic perspective available to us on Earth, difficult as it is to achieve, would have been even harder to reach from inside that void. Think about what it means for communication across the Boötes Void. Radio waves travel at the speed of light. Any signal sent from one side of the void to the other would take 330 million years to arrive. A civilization in one galaxy near the inner edge of the Boötes Void, sending a greeting toward a galaxy on the opposite inner edge, would be sending a message that would arrive during what, from Earth's perspective, would be the equivalent of the mid-Cretaceous period. The dinosaurs would not yet be extinct when the signal was sent. The signal would arrive in what was, for Earth, the deep past. No reply would be possible across cosmic time in any meaningful sense. The void does not merely separate galaxies by distance, it separates them by a kind of temporal unreachability that makes the concept of communication across its width essentially meaningless. The question of life inside the Boötes Void is speculative but worth considering. These 60-odd galaxies known to exist within the void are, by all indications, normal galaxies containing normal stars, normal planetary systems, and potentially normal conditions for chemistry. There is no physical reason that life as we know it could not exist in a galaxy inside the Boötes Void. The interior of a galaxy is largely insulated from the emptiness of the larger void surrounding it. Stars do not know they live in an unusual cosmic neighborhood. The physics of stellar nucleosynthesis, planetary formation, and organic chemistry would work the same inside the Boötes Void as anywhere else in the universe. Life, if it arose in one of those 60 galaxies, would look up at a slightly different sky but would be built from the same atoms, governed by the same laws. The galaxies inside the Boötes Void offer a scientific opportunity that extends beyond their role as markers of an unusual cosmic region. They exist in an environment so different from the dense clusters and filaments where most well-studied galaxies reside, that they serve as a natural laboratory for understanding how environment shapes galaxy evolution over cosmic time. In dense environments like galaxy clusters, galaxies experience a variety of processes that transform their character over billions of years. Tidal forces from neighbouring galaxies distort and disrupt stellar orbits. High-speed gravitational encounters heat the stars in galaxy disks. Hot gas filling the space between galaxies and clusters, the intracluster medium, rams into infalling galaxies and strips their cold gas in a process called ram pressure stripping. This stripping removes the raw material for star formation, causing cluster galaxies to cease forming new stars and age into red, gas-poor, elliptically shaped systems dominated by old stellar populations. The result is that dense environments are populated predominantly by quenched, passively evolving galaxies whose star-forming history ended billions of years ago. Void galaxies experience none of these transformations. They evolve in isolation, retaining their cold gas, continuing to form new stars, and maintaining the spiral morphology that characterizes younger, more active galaxies. Studies of void galaxy populations drawn from redshift surveys consistently find that galaxies in the most underdense regions are on average bluer, more spiral-dominated, more gas-rich, and more actively star-forming than the cosmic average. The galaxies of the Boötes Void belong to this broader class. They are, in a technical astronomical sense, among the most pristine examples of galaxy evolution available for study. Systems that have developed largely without the gravitational interference of neighbours, retaining characteristics that denser environments have largely erased from galaxies like the Milky Way and its companions. What would be different for life inside the Boötes Void is the isolation. Not the local isolation of an individual planet or solar system. The cosmic isolation of an entire galaxy sitting in a near-empty bubble of space. The nearest galaxy cluster would be hundreds of millions of light-years beyond the void's walls. Even if a civilization within the void developed spaceflight and radio communication, their knowledge of the larger structure of the universe would be harder to build, harder to interpret. The data available to them would show a universe with far fewer nearby reference points. Their surveys of large-scale structure would record a profound absence at the center of their observable universe, an absence they might struggle to explain. They would be, in a very real sense, more alone than we are. Not physically more alone in terms of the content of their own galaxy, but cosmically more isolated in terms of their relationship to the wider universe. Consider that the human civilization on Earth has, in roughly 400 years of modern astronomy, mapped the universe from the surface of a small planet orbiting an unremarkable star in one of hundreds of billions of galaxies. In 400 years, we have determined that the universe is 13.8 billion years old, that it contains 2 trillion galaxies, that it is expanding at an accelerating rate, that it contains structures spanning hundreds of millions of light years. We have done this from a single location, with instruments we built from metal and glass and silicon, using mathematics we invented ourselves. A civilization inside the Boötes Void, with the same capacity for curiosity and the same mathematical tools, would eventually arrive at the same understanding. But the void's emptiness would make certain observations harder and certain inferences less obvious. Completing the picture of the Boötes Void required observations from observatories distributed across both hemispheres and eventually from space. The Boötes constellation is visible from northern latitudes through much of the year, and the original surveys were conducted primarily from facilities in Arizona. But the cosmic web has no hemispheric preference. The full 3-dimensional structure of the universe, including the walls and filaments that bound the Boötes Void and give it context, extends across the entire sky. Southern Hemisphere observatories contributed their own redshift surveys of the sky south of the celestial equator, mapping the cosmic web in regions that northern telescopes could not access efficiently. The Anglo-Australian telescope at Siding Spring Observatory in New South Wales contributed extensive southern sky redshift surveys that complemented the northern hemisphere maps with measurements of galaxies in the southern galactic cap and adjacent regions. The resulting combined datasets, covering more than half the full sky, allowed cosmologists to trace the 3-dimensional architecture surrounding the Boötes Void with a completeness that northern-only surveys could not achieve. From these combined maps, it became possible to identify the wall structures that bound the void on multiple sides, to measure the density enhancements marking the void's edges from multiple angles, and to determine more precisely how the void shape compared to a simple sphere. The picture that emerged showed the Boötes Void connected on all sides to the larger filamentary network of the cosmic web, with concentrations of galaxies on its far side forming a loose shell visible in the data as an enhancement in galaxy density at the appropriate redshift range. The void was not merely a hole in the northern sky. It was a feature embedded within a global architecture that required global observations to characterize fully, and the combination of international observatories over 3 decades of effort was what produced the confident 3-dimensional picture of the void that exists today. What does the Boötes Void look like when you point a radio telescope at it? The answer is that it emits no significant radio signal from its interior regions. Radio telescopes can detect hydrogen gas, the most abundant element in the universe, through its characteristic 21 centimeter emission line. In the filaments of the cosmic web, hydrogen gas is everywhere. In the Boötes Void, radio surveys reveal a dramatic absence of the 21 centimeter signal from its interior. The void is not merely empty of galaxies, it is empty of the intergalactic gas and neutral hydrogen that is detected between galaxies in ordinary regions of the universe. Whatever evacuated the galaxies from the Boötes Void also stripped away most of the diffuse gas that would have filled the space between them. The void also exerts a measurable gravitational influence on the matter around it. Voids are under dense regions, which means their gravitational pull is below average. Matter on the edges of voids, caught between the pull of the void's slight underdensity and the stronger pull of the surrounding filaments and superclusters, tends to be drawn outward, away from the void and toward denser structures. This process, called void expansion, means that voids do not simply sit still over cosmic time, they grow. The matter on their edges flows outward, the void's interior becomes marginally emptier, and its effective radius increases over billions of years. The Boötes Void today is almost certainly larger than it was at the time the first galaxies formed. By the time the universe is twice its current age, the void will have grown still further, its walls having receded deeper into the surrounding structure. The intergalactic medium, the diffuse gas filling the space between galaxies throughout the universe, behaves very differently inside a supervoid like the Boötes Void than in the filaments and walls of the cosmic web. In dense environments such as galaxy clusters and the interiors of massive filaments, the intergalactic medium is heated to extreme temperatures, sometimes tens of millions of Kelvin, by a combination of gravitational shock heating as matter falls into deep potential wells, supernova-driven winds from massive stars, and the energetic output of active galactic nuclei. This warm, hot intergalactic medium contains a substantial fraction of the universe's ordinary baryonic matter in a state that is too hot to form stars but too diffuse to collapse under its own gravity. It can be detected through its emission of soft X-rays and through its absorption of specific ultraviolet wavelengths in the spectra of distant quasars viewed along lines of sight passing through it. Inside the Boötes Void, this warm, hot gas is dramatically depleted. The processes that heat and maintain it in dense regions were far weaker here, because there were fewer galaxies, fewer supernovae, fewer active nuclei, and the gravitational shock heating that accompanied structure formation was shallower by orders of magnitude compared to what occurred in dense filaments and superclusters. The intergalactic gas inside the void was never heated to the same degree, never compressed to comparable densities, and has been draining outward alongside ordinary galactic matter over the billions of years since the void formed. Radio surveys using the 21 centimeter emission line of neutral hydrogen confirm that this gas is dramatically underabundant in the void's interior relative to comparable volumes in denser regions. The void is not merely empty of visible galaxies, it is depleted, in a proportional way, of the full inventory of ordinary baryonic matter, including the diffuse gas that connects, surrounds, and feeds galaxies everywhere else in the universe. The temperature inside the Boötes Void is approximately what you would expect for the deep intergalactic medium, extremely low, on the order of a few Kelvin above absolute zero for the diffuse gas that does exist there, though the term temperature becomes complicated when you are dealing with near-vacuum conditions. There is no significant heat source inside the void to warm the sparse material that remains. The cosmic microwave background radiation, which permeates all of space at a uniform temperature of 2.7 Kelvin, fills the void as it fills everywhere. But beyond the background radiation and the occasional photon from a distant galaxy crossing the void, the interior is profoundly cold, profoundly quiet, and profoundly empty. It is, in one sense, the closest thing to absolute nothing that can exist in a physical universe. The human mind has a consistent difficulty scaling up from what it can touch and see. A mile is manageable, 1,000 miles is still meaningful. Even 1,000,000 miles, about 4 times the distance from Earth to the Moon, can be constructed mentally using a series of analogies. But the Boötes Void does not operate at any of those scales. It operates at a scale that is separated from everyday experience by a series of nested orders of magnitude that compound upon each other without end. Light travels 1 million miles in about 5.4 seconds. It takes light 100,000 years to cross the Milky Way. It would take light 330 million years to cross the Boötes Void. The ratio of the void's crossing time to a human lifetime of 80 years is more than 4 million to 1. The void is more than 4 million human lifetimes wide. The difficulty of comprehending cosmic scales is compounded by the way those scales are nested, each one building on the last in a chain of multiplications that quickly exceeds any analogy drawn from daily experience. Consider the full chain of distances leading to the Boötes Void. The distance from Earth to the Moon is roughly 250,000 miles, a span that a jet aircraft would take roughly 3 weeks to cross. The distance from Earth to the Sun is about 400 times that. The distance from the Sun to the nearest star is about 270,000 times the Earth-Sun distance. The diameter of the Milky Way is about 30 times the distance to the nearest star. The distance to the Andromeda Galaxy is about 25 times the diameter of the Milky Way. The distance from Earth to the near edge of the Boötes Void is roughly 280 times the distance to Andromeda. And the diameter of the Boötes Void itself is nearly half the distance from Earth to the void's near edge. At each step in this chain, the scale is individually incomprehensible by direct sensory experience. You cannot feel the Earth-Moon distance intuitively. You certainly cannot feel the Earth-Sun distance. The Sun to nearest star distance is already beyond any frame of reference the human nervous system is designed to navigate. By the time these individually incomprehensible intervals are multiplied together in a chain that terminates at the Boötes Void, the resulting scale is not incomprehensible in the way that 100 light-years is incomprehensible. It is incomprehensible in a higher-order sense, as the accumulated product of a series of individually impossible-to-grasp steps. The void does not merely sit far away. It sits at the end of a ladder of incomprehensible distances, each rung of which already exceeds what direct perception can hold. The galaxy count comparison is where the void becomes most viscerally strange. Imagine you are an explorer dropped at random coordinates in the universe. In an average region of the cosmos, you would expect to find a galaxy within 20 or 30 million light-years in any direction, and likely much closer. Galaxy clusters might present you with hundreds of galaxies within 50 million light-years. The universe is, on cosmic scales, densely structured. Now imagine you're dropped at the center of the Boötes Void. In any direction you would find almost nothing for 150 million light-years. Not sparse, not thin, almost nothing. The nearest galaxy you could see from the center of the void would likely be one of the 60 or so that cluster near the void's outer edges. Your neighborhood would contain approximately 3% of the galaxies that statistics predict for a comparable volume elsewhere in the universe. In 1986, 5 years after the initial discovery, the American astronomer Robert Kirsch-Neher described the Boötes Void in terms that have stuck with the field ever since. He called it a place where, if the Milky Way were located at its center, we would not have known about other galaxies until the 1980s. It is a remarkable statement. The history of human astronomy changed fundamentally in 1924, when Edwin Hubble established that the spiral nebulae were separate island universes, galaxies in their own right, lying far beyond the Milky Way. That discovery was made possible by the existence of observable galaxies within a few million to a few tens of millions of light-years of Earth. From inside the Boötes Void, those nearby reference points would not have existed. The nearest external galaxy would have been hundreds of millions of light-years away, detectable only by the most powerful modern telescopes. The cosmological revolution that happened in the 1920s might have been delayed by a century or more. Edwin Hubble resolved individual stars in the Andromeda Galaxy using the 100-inch Hooker telescope at Mount Wilson Observatory in 1923. Andromeda is approximately 2.5 million light-years away. The brightest stars in Andromeda could just barely be resolved at that distance with the instruments of the time, and from those observations Hubble inferred the galaxy's distance using Cepheid variable stars as standard candles. Now consider the nearest galaxy to the interior of the Boötes Void. Even if we assume a civilization inside the void builds a telescope equivalent to the Hubble Space Telescope, their nearest external galaxy would likely be 100 to 200 million light-years away, at the edge of the void's shell. At that distance, individual stars are invisible. The galaxy itself would be a faint smudge against the background. The precision needed to measure its distance would require instruments far beyond what we had in the 1920s, and the confirmation required to establish that this faint smudge was a separate galaxy would have taken much longer to obtain. There is a philosophical dimension to the Boötes Void that goes beyond its statistics and its formation mystery. The void exists as evidence of what the universe has chosen not to put somewhere. Cosmology deals mostly in the positive, in what exists where, how massive it is, what forces govern it. The void is a study in absence, in the physical reality of nothing, in the fact that emptiness has a structure and a history and a future. The nothing inside the Boötes Void is not the nothing of a mathematical abstraction. It is the physical product of specific gravitational and cosmological processes operating over billions of years. It is shaped, it is wounded, it is rowing. It has an identity as a cosmic structure, defined precisely by what is not there. In the philosophy of physics, the concept of vacuum has evolved considerably over the past century. Classical physics conceived of a vacuum as a region containing no matter, a passive absence of substance. Quantum mechanics changed this picture fundamentally. Even in the most perfect laboratory vacuum achievable, even in a region where every atom has been removed and every classical particle has been excluded, the quantum vacuum seethes with activity. Virtual particles arise and annihilate in pairs. Quantum fields fluctuate. Energy is present even in the absence of matter. The Boötes Void is not a quantum vacuum in this sense. It contains real galaxies, real matter, real fields, but the image it creates of a vast region defined by its emptiness resonates with this deeper physical truth that emptiness is never quite empty in the ultimate sense. Consider the energy of the Boötes Void. The cosmic microwave background radiation permeates it at 2.7 Kelvin, the uniform thermal remnant of the Big Bang that fills all of space equally. Dark energy, whatever its ultimate nature, acts through the void just as it acts everywhere else, driving the expansion of space within the void as throughout the cosmos. The gravitational influence of the void's sparse matter, while weaker than average, is not zero. The 60 or so galaxies inside the void contain billions of stars each, radiate energy, produce stellar winds, and maintain all the physical activity of ordinary galaxy life. The void is not truly empty even in the classical sense. It is merely emptier than anything we had reason to expect existed. The question of what the Boötes Void will look like in the far future is instructive. In 10 billion years, assuming the universe continues its accelerating expansion under dark energy, the void will have grown. The matter on its edges, pulled outward by the surrounding structures and repelled inward by nothing, will continue to drain away toward the denser regions of the cosmic web. The 60 galaxies currently inside the void may find themselves in an even emptier interior as the void expands. The outer shell structure may become more pronounced as the interior drains. In the very long run, if dark energy continues to accelerate the expansion of space, the universe as a whole moves toward a state of increasing emptiness, with structures becoming more isolated from each other. The Boötes Void is, in a sense, a preview of that future. It shows us what happens to a region of space when gravity fails to fill it, when matter departs and does not return. The future detection capabilities that will illuminate the Boötes Void further are already being built. The Vera C. Rubin Observatory in Chile, with its Large Synoptic Survey telescope, will conduct the Legacy Survey of Space and Time, a decade-long sky survey that will map billions of galaxies to unprecedented depth and precision. Its data will allow astronomers to trace the cosmic web with far greater resolution than current surveys permit, revealing the fine structure of void boundaries, the shell galaxies inside them, and the fine-scale galaxy distributions that encode information about dark energy and dark matter. The Euclid Space Telescope, launched in 2023, is mapping the large-scale structure of the universe across 10 billion light-years, specifically designed to test dark energy models by measuring how structure grows over cosmic time. These instruments will not solve the Boötes Void's formation mystery immediately, but they will provide the observational foundation on which solutions will eventually be built. What the Boötes Void ultimately teaches astronomers is that the universe is capable of producing surprises that exceed the predictions of well-tested models. This is not a failure of science. It is exactly what science is designed to encounter. A model that never produced a surprise would not be a model of reality. Reality, as we encounter it in the universe at large, includes structures at the edge of what any model predicts, phenomena at the limits of any framework, and occasionally features that require us to expand our conceptual toolkit rather than simply apply the existing one. The Boötes Void is one of those features. It has been in the data for more than 40 years, growing more precisely measured with each new survey, and it continues to generate productive scientific questions that have not yet received fully satisfying answers. There is something specifically meaningful about the scale of 330 million light-years in the context of Earth's biological history. That span of time as light travel time encompasses the entire history of vertebrate life on the land. The first amphibians had just begun their transition to terrestrial environments 330 million years ago. Everything that has happened since, every reptile, every dinosaur, every bird, every mammal, every human thought and human structure and human civilization fits inside the time it would take a photon to cross the Boötes Void. All of recorded human history, from the first cave paintings to the present, represents a fraction of a single second of the void's crossing time, not a metaphorical fraction, a literal, calculable, embarrassingly small fraction. Now pull back further and consider the Boötes Void in context of the 2 trillion galaxies estimated to exist in the observable universe. The void contains roughly 60 of them. That is 3 parts per 100 trillion of the total galaxy count, occupying a volume that should contain 2,000 galaxies. The void is a cosmic underperformer by an almost incomprehensible margin, and yet it is not unique. There are other large voids in the observed universe. None confirmed at its scale, but the distribution of void sizes suggests that the Boötes Void is at the extreme end of a real distribution, not a one-off anomaly. The universe at its largest scales is structured like foam. The filaments are the surfaces of vast soap bubbles, the voids are the air inside them. The Boötes Void is simply an extraordinarily large bubble, one whose walls are still being mapped and whose interior is still being catalogued decades after its discovery. The Boötes Void does not stand alone in the catalogues of large cosmic voids, though it remains among the best characterized and most confidently measured. Large-scale structure surveys have now identified thousands of distinct voids across the observable universe, ranging from the smallest detectable underdensities, spanning 10 to 50 million light-years, to the largest confirmed supervoids that challenge the predictions of the standard model. The statistical distribution of void sizes is itself informative. Small voids are numerically common, occurring frequently throughout the cosmic web, wherever matter has been evacuated from modestly underdense regions. Voids of intermediate scale, spanning 50 to 150 million light-years, are well understood within the Lambda-CDM framework and reproduced by simulations with reasonable fidelity. Large voids spanning more than 200 million light-years are progressively rarer, and their rarity steepens sharply with increasing size in a way that the standard model predicts, but that the Boötes Void strains. The IHRED Eschnus supervoid, by some measurements larger than the Boötes Void in linear extent, is shallower in its galaxy deficit and represents a different character of underdensity. The KBC void, which may encompass the local group itself, is vast but even shallower still. The Boötes Void's combination of extreme size and extreme depth, near total galaxy deficit relative to expectations, makes it unusual even within the catalogue of confirmed supervoids. Future surveys with the Virasi-Rubin Observatory and the Euclid Space Telescope will map the void size distribution to greater statistical precision, covering volumes of the observable universe many times larger than current surveys have reached. Whether those surveys find additional Boötes-scale voids at a frequency consistent with the standard model, or find them rarer or more common than predicted, will be one of the more informative tests of cosmological theory that the coming decade of observational astronomy will provide. The emptiness of the Boötes Void is one of the most powerful natural demonstrations of the concept of vastness at scale. Human beings have a robust intuition for the scale of their immediate environment. We are calibrated by evolution to navigate bodies, rooms, buildings, landscapes, continents. We have extended this intuition through technology to encompass the solar system dimly, and through mathematics to encompass the galaxy abstractly. But 330 million light-years of emptiness falls outside even the extended range of that calibrated intuition. It is a dimension of existence that we can access only through the mathematics of redshift spectroscopy and cosmological modelling, not through anything resembling direct perception. In that sense, the Boötes Void exists for us as a mathematical object that has been mapped onto physical reality, and the map is humbling beyond any attempt at casual description. The discovery of the Boötes Void changed the way cosmologists thought about the large-scale structure of the universe in a lasting way. Before 1981, the assumption of large-scale homogeneity, the idea that the universe, averaged over large enough spirals, is smooth and uniform, was somewhat taken for granted. The cosmic web was known to exist in rough outline, but the assumption was that the deviations from uniformity would be modest on the scale of hundreds of millions of light-years. The Boötes Void demonstrated that this assumption needed qualification. The universe could organize itself into structures, both dense and sparse, that were significantly more extreme than the models of the time anticipated. This realization drove the development of better models, better simulations, and a more sophisticated understanding of how the cosmic web assembles itself over time. The data from the Boötes Void has been used as a calibration point for n-body simulations of cosmic structure formation. When a simulation produces a void of comparable scale, cosmologists take note of the conditions that produced it, the particular configuration of initial density fluctuations, the role of dark energy in driving the expansion, the way gravity evacuates matter over time. These simulation results have sharpened our understanding of the sensitivity of a large-scale structure to cosmological parameters. The void is not merely a curiosity, it is a constraint on the physics of the universe. Its existence limits which cosmological models are viable. Its size and its galaxy deficit and its shell structure all carry information about the specific values of the parameters that govern cosmic evolution. One of the most striking aspects of the Boötes Void is how it was found, not through a dedicated search for voids, not through a program explicitly designed to look for extreme emptiness. It was found as a byproduct of an attempt to map the universe's structure. The astronomers were looking for what was there. What they found by its absence was something even more remarkable than any structure they might have charted. This is a recurring theme in the history of astronomy. The most important discoveries often arise not from finding the expected, but from encountering the unexpected absence, the signal that should be there and is not. The Boötes Void is the largest such absence ever catalogued. In the decades since its discovery, the Boötes Void has been revisited repeatedly by improved surveys. The 2-degree field galaxy redshift survey, the Sloan Digital Sky Survey, and other large redshift programs have each added data points, refined the void's geometry, and improved the census of galaxies within its boundaries. Each new survey has confirmed the basic finding of Kirsch, Neer and his team. The void is real. It is approximately the size originally estimated, though the precise boundary is not a sharp edge, but a gradual transition from extreme underdensity to the surrounding cosmic average. The surveys have also revealed that the 60 galaxy estimate for the interior population may still be a lower limit, as deeper surveys occasionally identify additional galaxies near the void's edges. The interior proper, however, remains as empty as the original measurements suggested. When you look at the full map of the observable universe's large-scale structure, the Boötes Void appears as a distinctive feature. The cosmic web, rendered in 3 dimensions from survey data, shows an intricate filamentary network against a backdrop of voids. Most voids in this map are modest in size, consistent with what Lambda-CDM predicts. The Boötes Void stands out. Its circular profile and cross-section, its depth of underdensity, and its position relative to surrounding structures are all immediately visible to anyone who knows where to look in the data. It is the universe's most prominent hole, and like any hole, it does not invite attention by what it contains, but by what it lacks. Think about the matter that should have been inside the Boötes Void but is not. Based on the expected density of the universe, approximately 2,000 galaxies worth of matter is missing from the void's interior. Each of those missing galaxies would, in an average region of the universe, contain perhaps 100 billion stars. Each of those stars would have its own retinue of planets, its own disk of gas and dust, its own potential for the chemistry of life. The matter that should have populated the Boötes Void, if distributed as it is elsewhere in the universe, would represent a catalogue of possibility far beyond anything in our immediate cosmic neighbourhood. None of it is there. The matter migrated away over billions of years, drawn by gravity toward the denser walls and filaments surrounding the void, leaving behind only the shell galaxies that trace its outer boundary. The void imposes itself on any attempt to think comprehensively about the scale of the universe. When we speak of the universe's 2 trillion galaxies, we are averaging over regions that include both the dense filaments and superclusters and the vast voids between them. The average, like all averages, smooths over the extremes. The Boötes Void is the extreme that the average hides. It represents the universe not as a smooth distribution, but as a deeply structured, deeply uneven distribution of matter and energy, with peaks and troughs that dwarf anything in human experience. The average galaxy density of the universe is, in the context of the Boötes Void, about as meaningful as the average temperature of the ocean, in the context of the deep polar trenches and the equatorial surface waters. The average is real, but it does not capture the range. The discovery also had a quieter legacy within the sociology of science. Before 1981, observational astronomy tended to operate under a de facto assumption that surprising structure at very large scales was unlikely. The cosmos was, at deep scales, expected to be boring, homogeneous. The Boötes Void ended that assumption definitively. Surveys conducted after 1981 were designed with greater care for the possibility of extreme structure. They used wider angular coverage, deeper sensitivity, and broader redshift ranges precisely because the void had demonstrated that the universe could hold surprises at scales that earlier surveys had not been designed to detect. The void did not just add a data point to cosmology, it changed the questions that cosmologists thought were worth asking. The boundary of the Boötes Void is not a wall. There is no sharp transition from emptiness to fullness at any specific location. Instead, the void grades gradually into the surrounding cosmic web over a span of many millions of light years. The transition zone contains galaxies at intermediate densities, neither as sparse as the void's interior nor as rich as the surrounding filaments. This gradual boundary is physically significant. It indicates that the void's edge is not a static feature but an active one, driven by ongoing gravitational processes that continue to shape the distribution of matter on its margins. The boundary is where the void is currently exerting its greatest influence on the surrounding structure. There is a kind of beauty in the structure of the cosmic web that the Boötes Void makes legible. The web is beautiful in the way that contrast creates beauty. The density of a filament is made meaningful by the depth of a void. The brightness of a galaxy cluster is made vivid by the darkness of the empty space surrounding it. The Boötes Void, as the most extreme available example of cosmic emptiness, sharpens the contrast of everything else. It defines the flaw of what cosmic structure can produce. Against that flaw, the richness of the cosmic web becomes not merely impressive but necessary, because the web and the void are not opposites. They are the same process, seen from its two extremes. Nothing in the solar system, nothing in the Milky Way, nothing in the local group provides any intuitive preparation for the emptiness of the Boötes Void. The void between solar systems in the Milky Way is already staggering. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. If the Sun were the size of a grapefruit, Proxima Centauri would be another grapefruit almost 7,000 kilometers away. That is the interstellar void. Now multiply that distance by the number needed to reach the scale of intergalactic space, and then multiply again to reach the scale of the Boötes Void. The compounding of these scales does not produce a larger version of a familiar thing. It produces something categorically different, something that exists in a dimension of scale the brain was never built to navigate. The 50% of the universe that exists in voids represents the other half of the universe's story from the half that exists in the cosmic web. The filaments, the superclusters, the galaxy clusters, the rich and intricate structure of the cosmic web occupy roughly half the universe's volume and contain essentially all of its matter. The voids occupy the other half and contain almost none of its matter. This is the fundamental asymmetry of cosmic structure. The universe is not uniformly distributed. It is not randomly scattered. It is organized into the most extreme possible binary, the very dense web and the very empty void. The Boötes Void is one of the universe's clearest declarations of that asymmetry. The visual representation of the large-scale structure of the universe, as rendered from redshift survey data in three-dimensional maps, makes the Boötes Void immediately apparent to anyone who knows where to look. Cosmologists typically color-code such maps by galaxy density, with bright regions indicating concentrations of galaxies and dark regions indicating underdensities or voids. In these maps, the filaments of the cosmic web appear as luminous threads, the superclusters glow at their nodes, and the voids appear as dark spherical or elongated regions embedded within the glowing architecture. The Boötes Void appears in such maps as a pronounced dark sphere, its interior nearly devoid of color, surrounded by a brightening ring where the galaxy density of the surrounding walls and filaments increases again at the void's boundary. Against the intricate luminous filigree of the cosmic web, the void is unmistakable. It is darker than the ordinary dark regions around it, emptier than the adjacent voids, and bounded with a geometry that reveals its approximately spherical character even in two-dimensional projections of the three-dimensional data. The visual impression it creates, a dark evacuated bubble set against the glowing foam of the cosmic web, is one of the most visually compelling in the literature on large-scale structure. The foam analogy that de la Pareeken and her colleagues introduced in 1986 to describe the cosmic web applies with particular force to the Boötes Void. If the universe is a cosmic foam, the Boötes Void is its most fully evacuated bubble, the one whose interior has been most completely emptied of the matter that glows on the surrounding surfaces. Looking at any map that captures it, you see not merely an absence of galaxies in one region, but the active structure of that absence, its boundary, its scale, its relationship to the filaments pressing in on all sides, and the shell of galaxies tracing its inner wall like a faint luminous rim at the edge of the largest dark space in the nearby universe. The distance from Earth to the Boötes Void, 700 million light-years, is itself worth examining. 700 million years ago on Earth, the Cambrian explosion had not yet occurred. Multicellular life was new. The first complex animals with eyes and bodies and behavior were just beginning their extraordinary experiment in form. The universe that those first complex animals swam through was not yet old enough in the direction of Boötes to have sent any light to Earth that we can detect today from the void's position. The light we detect from the galaxies at the void's edge left those galaxies 700 million years ago. It has been travelling through the expanding universe ever since. It carries information about a cosmos before complex life existed on Earth, and it tells us about a void that was already nearly as empty then as it is now. Now gather everything discussed so far and hold the full picture in mind. A sphere 330 million light-years across, 700 million light-years from Earth, 60 galaxies where 2,000 should exist, a crossing time of 330 million years at the speed of light, a formation history that strains the most successful model of structure formation in the universe, a boundary that is growing, that will grow further, that will continue expanding until the universe itself changes in ways we cannot fully predict. This is the Boötes Void, not a concept, not a theoretical prediction, a real measured, physical feature of the universe we inhabit. It was found by astronomers pointing telescopes at a strip of the sky and looking for what was there. They found what was not there instead, and that absence has been one of the most scientifically productive holes in any map of any kind ever drawn. What does it feel like to know the Boötes Void exists? Not to understand it in all its technical detail, but simply to know it is there. For some people, the knowledge produces a specific flavour of existential vertigo. The recognition that the universe operates on scales that remove the individual not just physically, but meaningfully from the centre of anything. You're not at the centre of the Milky Way is not at the centre of the local group is not at the centre of the cosmos, and all of this is situated in a universe that contains 700 million light-years away, a void so large that the distance light has travelled in the time vertebrate life has existed on Earth would not be enough to cross it. The vertigo is real, it is epistemically appropriate. For other people, the same knowledge produces something closer to wonder. The wonder is not in spite of the void's scale, but because of it. The universe, which could have arranged itself in any of an enormous number of possible configurations, chose this one. It built the cosmic web. It filled it with galaxies and stars and the precursors of planets and life, and it created the Boötes Void, not by accident but as the natural consequence of the same physics that created everything else. The void is not an error in the universe. It is the universe doing what it does at its most extreme on its largest canvas. To know that this canvas exists, to have mapped it from a single planet, from instruments built by creatures who evolved from single-celled organisms, is one of the most extraordinary facts of existence. The Boötes Void is a statement about scale, but scale is not the only lesson it contains. It is also a statement about method. We know the Boötes Void exists because of a 40-year series of careful measurements, each one building on the last, each one refining the picture that the previous measurements began. The original Kirch-Near survey used photographic plates and manual spectrum analysis. Modern surveys use digital detectors and automated pipeline processing. The tools changed. The method, observation followed by analysis followed by independent verification, did not. Science is not a single discovery. It is an accumulation of incremental improvements in the map, each one revealing more detail about a territory that has always been there. The Boötes Void was always there. We needed the map to find it. The scale of the Boötes Void makes it easy to feel that human existence and human inquiry are negligible. That is a possible interpretation. But there is another interpretation that is equally consistent with the data, and it is worth spending a moment with it. The Boötes Void is 330 million light-years across and utterly empty. You are 3 pounds of neural tissue, roughly 90 years of existence, on a planet the size of a grain of sand by cosmic comparison. And you measured it. You looked at a strip of the sky. You analysed the light that travelled for 700 million years to reach you. And you determined that a sphere 330 million light-years across contained 60 galaxies instead of 2,000. You built the map. The void has no awareness of being measured. The filaments of the cosmic web do not know they exist. Only you know. Only you can know. That capacity, whatever its scale relative to the void, is not negligible. It is the most remarkable fact the void has produced. The universe is not designed around human comprehension. That much the Boötes Void makes clear. The void did not form at a human comprehensible scale. It did not size itself to fit the range of any instrument we build, or any number we feel comfortable speaking. It is what it is, in its dimensions and its emptiness and its history, independent of whether any mind ever reaches a point of understanding it fully. But that independence is not indifference. The void is not hostile to understanding, it is simply vast. And vast things yield to the patient accumulation of measured data. Over 40 years, astronomers have been measuring the Boötes Void with increasing precision, and the portrait that emerges becomes more detailed with each survey, not less. The void cooperates with the instruments. It is in the business of being measurable, even if it is not in the business of being understood all at once. There is a sleep-relevant dimension to the Boötes Void that deserves acknowledgement. There is something deeply calming from a certain perspective about understanding that the universe contains spaces of such profound emptiness. The void does not require anything of you. It has no agenda. It is not moving toward anything. It is not happening at any particular rate. It is simply there. 330 million light-years of near nothing, cooling slowly from the warmth of the background radiation, growing slightly as its edges drain toward the surrounding structures, inhabited by 60 galaxies that have no knowledge of being exceptional. In its emptiness, it is one of the most peaceful structures in the cosmos. Not peaceful in the way a warm room is peaceful, peaceful in the way mathematics is peaceful, because it is exactly what it is, without any pressure to be anything else. The light from the nearest galaxies at the edge of the Boötes Void left those galaxies roughly 700 million years ago. It has been travelling through an expanding universe ever since, its wavelength being stretched by the expansion of space from ultraviolet or visible frequencies down toward the infrared end of the spectrum. By the time it arrives at our telescopes, it is reddened by the cosmic redshift shifted toward wavelengths our eyes cannot see but our instruments can. Every photon that reaches us from the Boötes Void is a message from 700 million years in the past, telling us about a universe before complex multicellular life emerged on Earth. We read that message with instruments that are themselves the product of the intelligence that emerged in the meantime. There is a circularity to this that is, if you sit with it, quite beautiful. The void's interior, to the best of current observational capability, is as empty as it appears. No hidden structures have been found inside it that would revise the galaxy deficit upward significantly. No dense cluster lurking at its centre, invisible to current surveys. No massive dark matter, concentration that might explain the evacuation of normal matter. Current instruments are sensitive enough to have detected any hidden galaxy comparable in luminosity to those at the void's edges, and none have been found. The void is what it looks like. A sphere of near emptiness in the fabric of the universe, as real and as measured as any galaxy cluster or supercluster that human astronomy has ever charted. When you think about the cosmic web as a whole, the Boötes Void occupies a specific place in the hierarchy of structures. It is a void, which means it is first order under density. It is bounded by the walls and filaments that connect to the denser nodes of the surrounding cosmic structure. Its void nature means it is growing. As the surrounding structure draws matter inward, the void's interior empties further. On timescales of billions of years, the void participates in the grand flow of matter from underdense regions toward overdense ones. A cosmic drainage system operating across scales that no telescope has fully mapped and no human life will span. The void is in motion, in the only way that something its size can be in motion, by its edges slowly receding outward while its interior grows emptier still. The relationship between voids and the cosmic acceleration is worth considering carefully. Dark energy, the mysterious energy associated with the fabric of space itself, drives the accelerating expansion of the universe. In dense regions, gravity counteracts this expansion, and structures like clusters and superclusters can maintain gravitational coherence even as space expands. In underdense regions like voids, there is less gravity to counteract the expansion, and dark energy's effect is relatively stronger. This means that voids expand faster than average regions of the universe. The larger and emptier a void, the more efficiently dark energy accelerates the expansion within it. The Boötes Void, as an extreme underdensity, is likely expanding faster internally than the average cosmic expansion rate. Its galaxy count will not increase over cosmic time. It will decrease as the few galaxies near its edges are gradually drawn away into the surrounding walls. There is a kind of logic to the universe's structure that the Boötes Void illuminates. The cosmic web is not an accident. It is the predictable result of physical laws operating over cosmic time. Gravity attracts. Dark energy accelerates expansion. Small initial variations in density amplify over billions of years into the intricate network of filaments, walls, nodes and voids that we observe today. Every void, including the Boötes Void, is the natural consequence of exactly the same physics that produced every galaxy cluster. The void and the supercluster are not opposites in any fundamental sense. They are the same process expressed in different initial conditions. Where matter was slightly denser to begin with, it became much denser over time. Where matter was slightly sparser, it became much sparser. The Boötes Void is the universe's most extreme statement of the second type of place. The question of what happens in the far future of the universe, under the continued influence of dark energy, is connected to the lesson of the Boötes Void. If the current model holds, the accelerating expansion will eventually cause all distant galaxies and structures to recede beyond the cosmological horizon, the distance at which recession speed equals the speed of light. Structures beyond this horizon become causally disconnected from us, unreachable even in principle by any signal. In the very far future, the only gravitationally bound structures that will persist are those that are already gravitationally bound today: individual galaxies, galaxy groups, and galaxy clusters. The cosmic web's filaments will dissolve, the universe will become increasingly empty and increasingly isolated. The Boötes Void is, in this light, a preview of a future in which all of space looks like its interior. As you lie here and let the numbers wash over you, there is no need to carry all of them consciously. Let most of them drift. What remains quietly beneath the mathematics is a simpler truth. The universe is enormous. Inside its enormity, there is a void 330 million light-years across that contains almost nothing. And on one side of that void, separated from its nearest edge by a distance that light takes 700 million years to cross, there is a galaxy containing a star with a small rocky planet where organisms evolved the ability to measure the void from across the distance. The measurement was made, the map was drawn, the number was verified, and now it is part of what is known, however quietly, by anyone who has spent time with it. The Boötes Void is not the last of its kind to be found. Future surveys will map the large-scale structure of the universe to greater depth and with finer resolution than anything available today. The voids they reveal will be charted more completely, their boundaries traced with greater accuracy, their interior populations catalogued down to fainter and fainter galaxies. It is possible that future surveys will find voids that rival the Boötes Void in scale, or that the precise measurement of the Boötes Void's dimensions will shift slightly as better data refines its profile. Science does not produce final answers, it produces better approximations of reality. The current answer, 330 million light-years of near emptiness at 700 million light-years from Earth, is the best available approximation. It is accurate enough to be genuinely astonishing. The Boötes Void is a gift to the scientific imagination in one sense that has nothing to do with its implications for cosmological models. It is a gift because it reminds scientists that the universe has not been fully anticipated. The best models available in 1981 did not predict it. The best models available in 2026 accommodate it at their limits but do not explain it fully. The void is a signpost pointing towards something that our current understanding has not yet reached. That signpost has been visible for more than 40 years. The physics it points toward is still being worked out. The map of the universe grows larger and more detailed with every survey. The Boötes Void sits in that map as a standing question, permanent and patient, waiting for the answer that the accumulation of observations will eventually provide. Let everything settle now. The numbers, the distances, the timescales, the galaxy counts. Let them drift into whatever layer of the mind holds things that are known but not constantly attended to. The Boötes Void will continue to exist whether you think about it or not. It will continue to expand, its edges slowly receding into the surrounding cosmic web, its interior growing fractionally emptier over timescales measured in billions of years. The 60 galaxies at its edges will continue their ordinary lives, forming stars, recycling gas, following the same physics as every galaxy in the denser regions of the universe, simply in a different neighborhood. The void does not know it is remarkable. It simply is what it is. An enormous, near-empty sphere of space in a universe that chose to organize itself this way. Somewhere between 700 and 1,000 million light-years from Earth, in the direction of the constellation Boötes, the cosmic web falls quiet. The filaments thin. The galaxies disperse. The density of the universe drops below the cosmic average, and then far below it, and then into a region where the distance between galaxies is measured not in millions of light years, but in hundreds of millions. The Boötes Void sits in that quiet region, having sat there for a very long time, long before any planet in any galaxy had evolved anything capable of wondering what lay in the dark between the lights. It is 330 million light-years across. It contains approximately 60 galaxies in the volume where 2,000 would be expected. It was found by 4 astronomers who were looking for what the universe contained and who found instead the most remarkable thing it does not contain. You can rest now. The void is not going anywhere. It will still be there when you wake, as it was before any mind in the universe knew of it. 330 million light-years of near nothing, patient and cold and vast, sitting in the dark between the lights of the cosmic web. Let the scale settle behind your eyes. Let the numbers become quiet. The universe is enormous, and inside its enormity, there is room for everything, including this. A sphere of space so empty that it took the most precise instruments humanity had ever built to confirm that it was not an error in the data. It was not an error. It never was. It is the Boötes Void, and it is real, and you know it is there. And that is one of the most quietly extraordinary things about being the kind of creature that can know anything at all.